Okay, so we're still in section 8-1, chapter 8, obviously, and this is recording number 3. Okay, so we're where I left off just now in the previous video, we talked about this. Samples are a specific size. You pick them out. The central limit theorem tells me that these x bars are going to have their own distribution, okay? And the example we used was the mean of the pulse rates as a random variable. Okay, it's very common. It's just what you'd expect, that the mean would not, in most cases, be exactly equal to the population mean of 82 beats per minute. Okay, so now if it's not equal, if that x bar is not equal to the 82, then there are two possibilities. Either the null hypothesis is true and the difference between the sample mean and the population mean is due to chance. Okay, so that's one possibility. The null hypothesis is true. There's no difference between taking this medication and not taking this medication. Any differences is strictly due to chance. If the x bar is different from what we expected, no big deal. It's just a matter of chance. Or the other possibility, the null hypothesis is false. The alternative hypothesis is what's going on. The sample came from a population whose mean is not 82 beats per minute, but is some other value. Unfortunately, we don't know what it is. Okay, so here's a cartoon that kind of illustrates this. Okay, so this is the cartoon for when the null hypothesis is true. So here's our distribution of sample means. Here's our x bars. Okay, and the mean of the population is 82. We got an x bar that's over here, okay? Well, so what? I mean, it's different from 82, but that particular x bar, it could be over here just by random chance. And that's the h sub 0 is true. That's this scenario. H sub 0 is false. What you're saying is, no, my friend. This x bar actually comes from a different population. This different population, which we don't know exactly what it is. We don't know what the mu is of this different population. We don't know what it is, okay? It's some population, but we don't know what it is. It has a different mu sub x. The x bar that we obtain by doing this experiment comes from this distribution, and this just kind of shows it pictorially in a nice visual way that the population that it comes from is shifted, in this case, is shifted over to the right. So what is this population? This is the population of everybody that takes that medication. This is the population of everybody that eats their Wheaties. I mean, whatever it happens to be that you're experimenting on, that's what the population looks like. It's shifted over. It's a different population. And that's why when we're talking about this, and we're doing the null hypothesis and we're doing the alternative hypothesis, that's why we use the symbol mu. So up here when we're talking about the medication, we're saying that mu, the population mu is 82. That's all of the human beings that are in our population. And we're saying our alternative hypothesis, mu is not equal to 82. Well, that's a different mu, right? I mean, that's not the mu of the entire population. That's the mu that we think is existing, and that's the population that took the medication. That's the population that ate the Wheaties, okay? So we are talking about two different populations. So when we're looking at these things, what we're trying to decide is this sample that you took out, does it belong to the original population, or does it belong to a different population? So eat your Wheaties, take your medication, you have the COVID antibodies, whatever the population is that you're talking about, you're saying that it is significantly different from the original population. That's your scenario here, where you're saying that the null hypothesis is false. Okay, So now, the farther away from the sample mean is from the population mean, well, that's more evidence, right? I mean, let's say, taking the pulse rate. If the average pulse rate for all human beings is 82, and you take this medication and now you have a pulse rate of 100, boy, you're going to be pretty convinced, right? But you still don't know until you do the statistical testing. But it's more evidence. You're kind of more convinced, okay? And what we're saying here is that that's more evidence that there would be for rejecting the null hypothesis. So what it's saying is the probability that that sample came from a population whose mean is 82, it decreases the further away you get from the original mean, okay? When you get further away this way or further away this way, you're probably going to say, you know what, I'm starting to be convinced that my null hypothesis is false, but I still have to do the testing to really confirm this. That's the essence of having a critical thinking on this. You don't want to just make guesses based on your intuition. You want to decide ahead of time what the criteria are, and then you make the decision. So this is done a million times. It's been done a million times in science. Okay, they set up the test, they do the experiment, and then they decide whether it meets the requirements or not. Okay. All right, so like here's an example here using that pulse rate business again. If it's 83, you'd say, well, that's not enough. That's 83, and the average is 82. Close enough for government work, right? Let's say it's 90. Then you say, gee, that seemed like that did increase the pulse rate. Okay, but is that scientifically sound? The question is, where does the researcher draw the line? Where do you decide? Okay, you don't decide based on intuition. You don't decide based on anecdotes. You have to have actual test data. Okay, so this is where we have this concept of statistical tests and level of significance. A statistical test uses the data obtained from a sample to make a decision about whether the null hypothesis should be rejected. Okay, the null hypothesis is pulse rates don't change. I take a sample of people that are taking the medication, and by golly, the pulse rate did change. It's at 90. That's my statistical test. I obtain the sample, and I use that to make a decision, okay? The numerical value that is obtained from a numerical test is typically referred to as the test value or the test statistic. So we're going to see here in just a few minutes, we're going to do this statistical test. It's basically a formula. We're going to come up with a number, and we're going to come up with a decision that will help us decide, do we reject the null hypothesis or not? Okay, so that's what he's talking about here. The mean is computed for the data, blah, blah, blah. And then you compare it to the population mean. So you have a sample that you compare to the population. Then a decision is made to reject or not reject the null hypothesis. And that's based on the value obtained from the statistical test. If it's significantly different, then you reject the null hypothesis. If it's not, then the null hypothesis is not rejected. So it's this concept that, who has the burden of proof? The H sub 1, the alternative hypothesis, it has the burden of proof. You have to reject the null hypothesis. If it's not significantly different, you do not reject the null hypothesis. Okay? As previously stated, the sample data are used to determine if a null hypothesis should be rejected. Okay? So now, you're basing this on sample data. You're going out there and you're feeding Wheaties to a bunch of kids. You're taking people and you're giving them this medication. There's still a possibility of making an incorrect decision. It's never going to be absolutely guaranteed. Okay, but that's just the way it is in life. Okay, so there's 4 possible outcomes. All right, so this column here is this scenario where the null hypothesis is true. The null hypothesis being that the mu of the pulse rates is equal to 82. This column here is where the null hypothesis is in fact false. So this, when we're talking these guys, these columns, this is like absolute truth. You know what the truth is. You know that it's true. You know that it's false. Okay, you know that the null hypothesis is true, or you know that the null hypothesis is false. Now, obviously, in real life, you don't have that situation, but this is to help us understand this concept. Okay, so now where can you make mistakes? Well, you can reject the null hypothesis, but in fact, the null hypothesis is true, but you rejected it. That's a mistake. You could not reject the null hypothesis, but it turns out that the null hypothesis was false. So that's a mistake, right? So there's two types of errors that you can make. You don't reject, but you should have. That's this column here. You do reject, you reject the null hypothesis, but the null hypothesis was true, so you made a mistake. So that's why they say these two guys here, those are the errors, type 1 and type 2 errors. These are correct decisions. Here you do not reject the null hypothesis. You do not reject it. Well, that's a good decision because the null hypothesis was true. Here you do reject the null hypothesis and the null hypothesis is false, so that was a correct decision. Okay, so I let you read that, but that's my overview of what's going on there, okay? So type 1 error, you reject the null hypothesis when it is true. Type 2, you do not reject when it is false. Type 1 is kind of the one we're going to always be using here. They call that the beta. Okay. All right, so using our situation that we had, the situation A, maybe it doesn't reject the pulse rate. Okay, maybe the sample, it just changed the rate by chance. Okay, you reject the null hypothesis and it's really true. That's a type 1 error. On the other hand, the medication might not change. Okay, it might not. It might cause a significant increase or decrease in the pulse rate of users. So the researcher, on the basis of the data obtained from this sample, will not reject the null hypothesis, a type 2 error. So type 2 error, you did not reject, but the null hypothesis is false. So run a couple of scenarios by in your own alleged mind, and you'll be able to get this distinguished, okay? It's a little bit confusing when you first see it. So take a look at all these different examples, and I believe that it'll make more sense, okay? Okay, so now what is the level of significance? That's going to be our next topic, okay? So let's defer that to the next tape. I'm going to end this recording right now.